Hello, everyone. This is the first in a series of short tutorials about the fundamentals of solid-state physics. This tutorial is intended for new students that maybe haven't taken a solid-state physics class before, but are embarking on research in a condensed matter lab. So the first lecture is about fundamental crystal lattice systems. So, solid-state physics can be roughly described as the study of crystalline solids. So that begs the question, what is a crystal? So colloquially, we might think of a crystal as being something that is sparkly or transparent, like this piece of quartz right here, or this diamond right here. And these are examples of crystals, but they're not the only examples of crystals. So scientifically, the definition of a crystal is a material where you have a regularly repeating arrangement of atoms. And I'm going to quantify this statement in the rest of this tutorial. But for now, I just want to describe the diversity of crystals that exist. So the one over here is rock salt. This is sort of the scientific name for table salt. And you can see that it has a square shape, each of the little crystallites, and this reflects the underlying cubic symmetry of the atomic arrangement in this material. Another material that you might have seen before that sort of has a very specific shape is iron pyrite or fool's gold. And again, the external shape of the crystallites reflects the internal microscopic structure. So crystals can be found in nature, or they can be synthesized in a factory or a lab. So in the latter case, these are silicon ingots, I think they're called. So they're grown really large. This would actually be as large as a person if you were to have a person standing next to it. And then it's sliced into wafers to make semiconductor devices. And then in my lab, we study lots of different crystals that are synthesized in small batches, and they do not take the form of 12-inch wafers. They take the form of little millimeter-sized crystals. All right, so there are a lot of crystals out there, and let's get into sort of the vocabulary and the math that we use to describe them. So the first vocabulary word that I want to, whoops, sorry, my app closed. All right, so hopefully this will work. All right, so I'm just going to give a little bit of vocabulary. So the first vocabulary word is lattice. So lattice is a mathematical grid of regularly repeating points. All right, so a lattice is a mathematical object, and then on top of this lattice, one can put a basis. So a basis is a physical object. It is an atom or group of atoms that is attached to each of the lattice points. All right, so taken together, the lattice plus the basis gives the crystal. And in a little bit, I'll go into some detail about how this happens. But before that, let me describe a little bit more vocabulary. So the next vocabulary word is primitive lattice. And this is a set of all lattice points with the following position vectors. So the position vectors of these lattice points are given by U1, which is an integer, times A1 plus U2, A times A2 vector plus U3 times A3 vector. Okay, so here U1, U2, U3 are integers, and then A1, A2, A3 are primitive translation vectors. And these primitive translation vectors can be used to construct a grid with all the lattice points. And this is a lot clearer in pictorial form as opposed to verbally. So let me show a picture of that. So here are a couple of um, examples, two of which feature primitive translation vectors and one which does not. Okay, so the red points comprise a grid. They comprise a lattice, and uh, and uh, in this portion of the sketch, A2 and A1 are the two primitive translation vectors. So this is a two-dimensional picture, so we only have two primitive translation vectors as opposed to three in the equation that I wrote down for three dimensions. So in this sketch, A1 and A2 are one set of primitive translation vectors that you could choose. So you can see for yourself that if you start off at this point right here and label that as the origin, you can sort of produce the entire grid by basically translating an integer number of times with the A1 vector and translating an integer number of times with the A2 vector. You can produce the entire grid that way. The choice of primitive translation vectors is not unique. So for example, A1 prime and A2 prime, they are also primitive translation vectors. They're not the most obvious choice of that, but they are primitive translation vectors. You can use A1 prime and A2 prime to also produce all of the points in this lattice. However, this image here, that here, A1 double prime, that is not a primitive translation vector because you can see that it's just twice A1. And if you were to start at this origin point and you then tried to tile or tried to produce this lattice using these two translation vectors, A2 double prime and A1 double prime, you would not be able to do that. You can see that visually where here, this horizontal line, it skips this point right here. So this is not a primitive translation vector, but these two are, and these two are. Okay, so the next, and I think this is the last definition I'm going to write down for now. The primitive cell or the primitive unit cell is the parallelepiped, which is just a three-dimensional generalization of a parallelogram. So it is let me just write down that word so I can take my time with it. So it is a parallelepiped defined by the D primitive translation vectors in D-dimensional space. Okay, so basically in two dimensions, it's going to be some sort of two-dimensional parallelogram. In three dimensions, it's going to be some sort of three-dimensional parallelogram. So I'll get back to some attributes of the primitive cell, but let me just go back to the picture up here. So this gray parallelogram that's defined by the vectors A1 and A2, that is an example of a primitive cell. This gray parallelogram which is defined by A1 prime and A2 prime, is a different primitive cell. This parallelogram is not a primitive cell because it is not defined by primitive translation vectors. So let me go back here. So some properties of a primitive cell are the following, and I'm writing these down because if you ever need to construct a primitive cell, you might be a little bit misled by something that looks like it's primitive, but it's not. So these are just things to double check. So properties of a primitive cell are the following. So it only contains one lattice point. Oops, I think sorry, ignore this, one lattice point. All right, so one caveat of this statement is that depending how you construct your primitive cell, you might have the one lattice point being shared amongst adjacent primitive cells. So specifically, if we just look at this parallelogram right here, the first one, you can see that each of the red circles, it's sort of shared by four adjacent uh, uh, parallelograms. So inside this gray parallelogram, it only has 1/4 of this lattice point, but it has four lattice points at each of one at each of the corners. So 1/4 times 4 is 1. So this is just a reminder that if you have a lattice point either on the edge or on the corner of your primitive cell or your unit cell, more generally speaking, um, then uh, then you need to think about how many adjacent cells is this corner point being shared with. Okay, so that is the first property. The second property is that it can be used to tile all of space. Okay, so you can see that these parallelograms, they can be used to tile all of space, both this one and the other one that comprise primitive cells. So it should be noted that this attribute of a primitive cell is not an attribute that is only true of a primitive cell. So this one on the right that is not a primitive cell, it can also be used to tile all of space. So the second thing that I wrote down is necessary but not a sufficient condition. And then the last attribute is that the volume of the primitive cell is the smallest possible volume that can be used to tile all of space. And this is sort of an elaboration of the statement I made about the non-primitive cell. Um, so, uh, uh, so it's the smallest volume that can be used to tile all of space, and it has the following volume. So if you know what the if you know what the primitive translation vectors are, then the volume of the shape that they enclose is given as the absolute value of A1 dot A2 crossed with A3. And obviously the order doesn't matter because we're taking an absolute value here. So this is the formula in 3D. In 2D, the formula is equal to the absolute value of A1 cross A2. Okay, So, so these are attributes of a primitive cell. And then the next question is, how do you go about constructing um, a primitive cell? So one approach that you can use is sort of guess and inspection. So you can sort of guess the shape that sort of can be used to produce the entire lattice, and then check that this shape only contains one lattice point. So, just looking at this arrangement of lattice points here, probably this set of primitive translation vectors, the simplest one, is the one that you might choose instinctively. And then you would choose this and then use it to construct a parallelogram and then see, okay, does this parallelogram only contain one point, considering the fact that all the corner points are shared by 4 other cells. So that's sort of the guess plus inspection method. The other method that you might use, which is sort of more deliberate, and it's going to come in handy a little bit later on um, for producing Brillouin zones, which are sort of structures in reciprocal space that I won't be getting into here. But anyway, the sort of more formulaic method is called the Wigner sites, whoops, sites cell. And this is a specific method for constructing a primitive cell. So let me just I'll draw it for a uh, sort of hexagonal lattice. Okay, so this is supposed to be 6 points in a hexagonal lattice. Sorry, it's not drawn uh, very accurately, but the procedure is as following. So first you pick one of the lattice points, and obviously there would be a lot more in the picture if we were doing this for real, but you would pick one lattice point, and this is your central point. So then you draw lines connecting to all the nearby points. So let's connect this to all of its neighbors. All right, so now it's connected to all its neighbors. And then you draw a perpendicular bisector through all of these lines that we just drew. Okay, so perpendicular bisector, perpendicular bisector, perpendicular bisector, another perpendicular bisector, and you just connect them all up, and then the shape that they form, the closed shape that they form is the Wigner site cell, which is a type of primitive cell. And by this procedure, it automatically has only one lattice point inside. Okay, so so this is the general idea of the primitive translation vectors and the primitive unit cell. So at this point, I want to return back to this concept right here, the idea that a lattice plus a basis equals a crystal. So now that we have the vocabulary that follows it, we can properly discuss this issue. Okay, so so here are examples of some regular arrangements of atoms where the dots, as they are drawn, do not represent a lattice. They represent a lattice plus a basis. So the first example is sort of uh, an extension of the image on the previous slide, where the points of the lattice have a similar arrangement to that picture, but instead of just a point there, there's actually 2 atoms that are stuck to each of those lattice points. So our primitive translation vectors, I'm going to write this one as A2, and this one right here that's horizontal as A1. So those are our 2 vectors, and we can still use those 2 vectors to reach all of the points in our lattice. The points in the lattice are the little pink dots that I drew by hand. But then on top of each of those lattice points, there are 2 atoms that are a little bit offset from the lattice points themselves, and those 2 points are put on top of every single lattice point in the exact same way. So these two atoms, they are the basis. Together, they are the basis. And then the regular arrangement of atoms, where you have your basis sitting on top of each of the lattice points, that forms this first two-dimensional crystal that I drew. Another example I have here is one that you might encounter. So this is called a honeycomb lattice for obvious reasons. And you might think that each of the points here is a represents a lattice, represents a primitive lattice. So this is not the case, and this is an example where each of these hexagons, it can be used to tile all of space, but each of the points on the hexagon do not represent a primitive lattice. And you can see that for yourself in a number of ways. So one way to see it is if you look at this point right here where I just drew the arrow, you can see that it has another atom directly to its right. However, this other point, which you might think is identical at first glance, if you look more carefully, you can see that it does not have an atom that is separated by the same distance. Let's call this distance A from the first that this one has. So basically, there's no atom right here as you would have if this point were representing sort of a direct translation of this point. So in a honeycomb lattice, um, there is a two-atom basis, and one way of defining the basis is shown here. So just two atoms that are adjacent to each other horizontally. And one way of defining primitive translation vectors is drawn in with the green parallelogram, where let's call this lower one A1 and this upper one A2. Okay, and you can see for yourself that this basis of two horizontal atoms, if we start sort of in their central point, translate by A2, we end up at another central point with the same basis rounded. And you can repeat this exercise to convince yourself that indeed this is one choice of primitive translation vectors that properly captures this honeycomb lattice. So let me do one more vocabulary, and I'll do it on this slide. And that vocabulary, and this is one that's actually used a lot in research, this vocabulary is a unit cell. And I threw that word in earlier without defining it, but a unit cell is the smallest or sometimes most convenient repeating unit which comprises a crystal. So it consists of a lattice and a basis. And in these two pictures that I have here on this graph, the green parallelograms represent one choice of unit cell. And uh, yeah, so what else did I want to say here? Yeah, so I just want to emphasize that unit cell is the vocabulary word that you will most often encounter when you talk to solid state physicists, when you read papers, when you see figures in papers. And this is the word that you should remember. So the unit cell is really what comprises the repeating unit in a crystal. The vocabulary introduced previously was sort of preliminary information to understand a unit cell. But the unit cell is the word that you really need to know. Okay, so I'm almost done. This is a fairly straightforward lecture, just a little bit of information. So because of constraints of space, there are sort of uh, 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 a limited choice of the lattices that can exist. So there are not infinite types of lattices that can be constructed and still following the rules of being a primitive lattice. So the word Rabi lattice, it also means primitive lattice. So in two dimensions, there are only 5 Bravais lattices, and this is just the lattice. It says nothing about sort of the basis. It says nothing about the unit cell, but in two dimensions, going from highest symmetry on the right to lowest symmetry on the left, you have, um, so the T here stands for tetragonal, so it's sort of a square lattice. The H stands for hexagonal, and hexagonal lattice sort of has uh, the two primitive translation vectors having the same length, and the angle between them is 120 degrees. I forgot to mention that for the tetragonal or the square lattice, the two primitive translation vectors are the same length, and the angle between them is 90 degrees. So O stands for orthorhombic, and also they can be called rectangular. And there are sort of two types of rectangular lattices. One that is rectangular, what you would usually think of a rectangular lattice, 90-degree angle, but then the two translation vectors do not have the same length. But then there's a centered version down below, which is labeled with the number 3. So it should be, so let me come back to that in a little bit. And then the least symmetric one, the M here stands for monoclinic, and that means that the translation vectors A and B do not have the same length, and then the angle between them is not 90 degrees. Okay, so one comment that I want to make in this O column regarding the centered one is that there is sort of a primitive, sometimes there is a primitive cell that is different from what is called a conventional cell. So in this lattice that's labeled 3, the primitive translation vectors, one choice of them is vector C and vectors D. However, sometimes it's more convenient to work in a system where all of the angles are 90 degrees if you don't care that it's a primitive lattice or not. And there you would have a sort of a rectangle with another atom in between, and you can count for yourself that there is more than one lattice point in this conventional cell shown here. So each of the corners is 1/4. So 4 corners gives 1 atom, and then there's 1 in the center that's completely inside. So that is 2 atoms in this unit cell. And this is the conventional cell, sometimes more convenient to use. And this one right here, defined by C and D, is the primitive one. All right. Another thing that I want to point out here is the labeling. So the crystallographic axes are often called A, B, and C, where C is traditionally, so though not always, along the z-axis, so not relevant to this drawing. Another sort of tradition in the field is that the spacing between two lattice sites without, if it doesn't have a specific label, it's usually called A, no matter what direction it is. The smallest spacing is sort of traditionally called A. Okay, so this is the Bravai lattices, the primitive lattices that exist in 2 dimensions. There's only 5 of them. In 3 dimensions, there are only 14 of them, and they are shown here. And again, they're sort of grouped into cubic, tetragonal. So cubic has all 3 sides equal, and tetragonal has sort of the base is a square, and then it's a prism where the third length is not equal to the size of the base. The next one is orthorhombic. So again, we're moving from higher symmetry to lower symmetry. There is a hexagonal lattice, a trigonal system, which is related, monoclinic, and triclinic. And on this graph, like I said, as you move down, they get less and less symmetric. I want to again point out that in the cubic system, you have 2 examples of primitive cells, of conventional cells that are not the primitive cell. So this one right here in green is called body-centered cubic, BCC, and it has an atom in the center of the cube, and you can count for yourself. So there are 8 corner atoms, which are each shared by 8 adjacent cells. So that's 1 atom, and then 1 more in the center. So that's 2 in the primitive in the conventional cell. So this conventional cell is not a primitive cell. You can write a primitive cell for the BCC structure that'll look different from this drawing, but oftentimes it's more convenient to work in sort of a cubic system. So this same statement also applies for face-centered cubic, which is called FCC. And here you have a lattice site or an atom at the corner or at the center rather of every face. So there are 6 faces on a cube, and each of those face atoms is shared among 2 adjacent cells. So that gives a total of 3 atoms in this unit cell from the faces, and then an additional 1 for from the corners. So the FCC structure has a total of 4 atoms in the conventional unit cell, which is not the primitive cell. What else can I say here? So some of these crystal structures are what are called closed packed structures, which means like the name implies, it's sort of the closest that atoms can get together. So imagine you have ping pong balls, and you sort of arrange them in a kind of hexagonal lattice like this picture here. And then you want to stack, you have layers of them, and you stack them on top of each other. So the next layer will most comfortably sit, for example, like this. And then you do this over and over again, just sort of put every next layer into the lowest point between 3 atoms in the layer below, and that gives you a closed packed structure. So the FCC structure, if you slice it along the diagonal, is actually a closed packed structure. So it consists of layers just like this, stacked in a specific way. And what else do I want to say about these? Yeah, so uh, mm, so the cubic crystal structure is okay. So I guess what I do want to say about this is that most of the metals on the periodic table are either BCC or FCC. One of those. A simple cubic structure is actually only realized in polonium, but yeah. So Every three-dimensional crystal that exists, it can be constructed from these 14 Bravai lattices by basically putting regular arrangements of atoms onto each of the lattice points that are indicated in this drawing by dots. Um, so there is also the topic of space groups, which I won't get into here, but there are 230 space groups, which basically uh, um, uh, describe sort of different symmetry operations that you can do in translation and rotation and whatnot to produce every crystal that exists. All right, so that is all that I want to say um, about crystal systems. So just to recap, the definition of a crystal is that you have a regularly repeating arrangement of atoms, and the structure that regularly repeats is what is called a unit cell. And a unit cell is sort of the smallest or the most convenient way to fully describe the repeating unit in a crystal. So it contains information about the lattice, it contains information about the basis. And that's it for this tutorial.